In this video, we're going to start section 7.2, which is on finding volume. So for our first video, we're going to find volume using the disk method. So we have used the integral to find the area of a region under a curve, and we just practiced that in section 7.1. And of course, most recently, the area of a region between two curves. And what we want to do now is we want to think about a two-dimensional object rotating about a line. So as you can see, and I am no artist, so looking at this picture, I have a radius of r and a width of w. And so that corresponds to the same distances on my picture. And essentially what I'm doing is I'm taking this rectangle and I think about pushing it back over the line, and so it's going to just rotate about that line to make it look like a disk. Now, if we have a consistent width and a consistent radius, it's very easy to find the volume. We can just use the formula for finding the volume of a disk, which is pi times r squared, which of course pi r squared is just the area of a circle. So if you can try to think about taking this circle times the width, and so think about however many circles it would take to create that width, but we're taking just a circle and essentially we're stacking it. So very easy if we have a disk that looks like this. Obviously, this is a Calculus 2 class, and so we're not going to have a disk that looks like that. So we're not going to have a consistent radius. We're going to have something that is curved. And as you can see, I didn't draw the curved figure, but if you think about this as a figure that would have a changing radius on each side, and that's the kind of figure that we're talking about. And so in Calculus 1, when we first started to learn about integration and finding the area under a curve, we did a method like the trapezoidal method, which would obviously work really well here. Or we just created rectangles, and then we created more rectangles and more rectangles and more rectangles until we started talking about the limit as the width of that rectangle approached 0 being the actual area of the figure. So that's what we're going to do here, is we're thinking about that same formula that I had before, which was pi times r squared times the width. And notice what I've done is I'm talking about the norm, and we talked about the norm before in Calculus 1. Essentially, we're talking about the changes or the differences in the widths. As that difference becomes 0, approaches 0, for I equals 1 to n, meaning for all of the different widths, all of the different radii, and all of the different widths. So if I have more and more and more and more and more radii, then obviously delta x is that change in x. It's the delta x, the width, the change in the width of the figure. That's all I'm doing. So notice I still have pi, I still have r squared. I kind of covered up the squared there, but I still have r squared, but we're just saying for each x value. So the width, the radius at each x value, and then delta x would be the width. Anyways, as that limit of the width approaches 0, I end up with the integral from a to b. So obviously in this case, this would be a, this would be b, this would be a, this would be b. And I'm just integrating. Again, pi is on the outside. I've replaced r xi squared with r xi squared, and then delta x becomes dx because I am integrating with respect to x. So as long as we're dealing with a horizontal axis of revolution, which is what we're going to focus on to begin with, this is my formula. And then we'll talk in just a little bit about what happens when I rotate around the y-axis instead. But this is the formula that we are going to use. So let's take a look at an example, and I've pre-done a little bit for you. And again, I'm no artist, I'm just trying to help you visualize what's going on. So this one asks us to find the volume of the solid formed by revolving the region bound by the graph of f of x equals 1 minus x squared and the x-axis about the x-axis. So as you can see, I've taken the graph, and again I've just used Desmos to graph this. And it says using that line and the x-axis. So that region that I've colored in yellow is the region that we're talking about. And we're saying, hey, if I rotate that about the x-axis, again, what's going to happen is it's going to sort of reflect over here. So obviously this looks 2D, but this is a 3D figure. Again, so how am I going to solve this? Well, the first thing I need to do is I need to find the limits of integration. And again, just like we did in section 7.1, I'm going to take my 1 minus x squared and set it equal to the other line, and in this line that is just going to be 0, y equals 0. And then I'm just going to solve this, which is going to be very easy. So I get x squared equals 1 by adding x squared to each side. By taking the square root, I get x equals plus or minus the square root of 1, and the square root of 1 is 1. So it's just plus or minus 1, which means now I'm going to integrate. So step 1 really is to visualize. So draw the picture, visualize what it is that you're going to be finding. Now I'm going to integrate, and again I'm going to just use that formula, and my formula said to take pi, and then my limits of integration, which I just found, -1 to +1. And again, we could have cheated on this one, as you know, -1, +1, but you should always mathematically find those values. And then I'm going to integrate that function. So the function is 1 minus x squared, again because r is the function 1 minus x squared, and I have to square r, and then dx represents that changing width. Now obviously I could just get my calculator out and let it solve for me, but this is a calculus class, and so I am going to want to see that you are able to, math it up a little bit. So again, I'm integrating from -1 to +1 of this function squared, so I'm going to square that function. That's going to give me 1 minus 2x squared plus x to the 4th dx. Now I can integrate. So 1, using the power rule, becomes x, minus 2x squared becomes minus 2x cubed over 3, and plus x to the 4th becomes plus x to the 5th divided by 5. Again, just using that power rule, going from -1 to 1. Notice I'm choosing to keep this pi on the outside. That is your best practice there. Don't use it till you get to the end. Again, continuing using +1 first. Again, I'm going to keep the pi on the outside. I'm going to go ahead and use a bracket since I'm going to have parentheses on the inside. 1 minus 2 times 1 cubed over 3, so that's minus 1 over 3, plus 1 to the 5th over 5, which is just 1/5. I'm subtracting, and now I'm going to repeat for -1, so -1, and then minus 2 times -1 to the 3rd over 3 gives me plus 2/3, and then plus -1 to the 5th over 5 gives me minus 1/5. And then doing some simplification, and I'm kind of running out of room here. I wish I would have left myself a little bit more room. But again, you can use your calculator to help you, or just use your brain, because hopefully you know how to, combine fractions. So if I combine the 1, and again, we've talked before about make sure you understand that subtracting everything. So a lot of people go through and try to cancel things out. They shouldn't. Here I've got 1, and 1 gives me 2, minus 1/3, and minus this should be a 2/3, I'm sorry. Minus 2/3 and minus 2/3 gives me minus 4/3, and then plus 1/5 and plus 1/5 gives me plus 2/5. If I combine all of those things together, I get 16/15 pi. So what's my solution? 16/15 pi, or I can obviously estimate that 3.351. So just pay attention to the instructions. If they're okay with an estimate, I could have actually skipped all of this work and just plugged it into my calculator, and that would give me this estimate. But typically, at least in my class, I'm going to look for that exact value as well. Let's look at an example now involving a trigonometric function. So here I have the function of sine of x, and I'm taking the volume formed by that function and the x-axis in the interval from 0 to pi about the x-axis. So lucky us, we don't have to do any solving for the limits of integration. I know to find the volume, I'm going to take pi, and then again from 0 to pi of sine of x squared dx. Now on this one, way easier to just use your calculator, but we should not shy away from doing the math, and that's what we're going to do. So if I'm going to integrate sine squared, and again you could write this instead as sine squared x, notice those two are the exact same thing. We have to remember some things that we know from Trig and from Calc 1. So I'm going to just create a separation here. If I know cosine of 2x, and this is just a trig identity, is equal to cosine squared x minus sine squared x. I also know that cosine squared x plus sine squared x is equal to 1. So if I try to get cosine squared x alone, I would end up with 1 minus sine squared x is cosine squared x. So I'm going to take this expression and replace it over here for cosine squared x. So cosine of 2x is equal to 1 minus sine squared x by substitution, and then just bring down the minus sine squared x. So reducing this a little bit, cosine of 2x is equal to 1 minus 2 sine squared x, because there are two of them. And now, because I want to get sine squared x by itself, I'm going to end up with cosine of 2x, 1 minus cosine of 2x is equal to 2 sine squared x. Again, by just adding, subtracting, etc. And now I want to get just sine squared x, so I'm going to take everything divided by 2. So 1 over 2 minus cosine of 2x over 2 is equal to sine squared x. And now keep in mind, I could have just taken that 1/2 to the outside and left this as 1 and cosine 2x. So what I'm going to do up here is now I'm going to replace sine squared x with 1 minus cosine of 2x. So why did I do all of that? Because it's really difficult to integrate sine squared x. That's why we had to do all of this, so that we can integrate something that we can actually do. So what I end up with now is, oops, I forgot my 1/2. Come on guys, help me out here. Let's put the 1/2 in front of the pi, so 1/2 pi and 1/2 pi. So by integrating 1, I get x. By integrating cosine of 2x, I get sine of 2x. But the problem with sine of 2x is, remember, when we do the chain rule, when we differentiate, we have this 2 here, so that means I'm going to have to divide by that 2. And again, this is from 0 to pi. So what I have now is the volume, which is 1/2 pi, and then I have pi minus sine of 2 times pi over 2 minus 0 minus sine of 0 over 2. Oops, sorry. Sine of 2 times 0, which of course is sine of 0 over 2. That gives me 1/2 pi. Reducing what's inside, I have pi minus 0 minus 0 minus 0. And then, of course, that's going to give me my solution. 1/2 times pi of 4.9348, or of course, pi squared over 2 would be my exact solution. Let's change things up just a little bit. This is still the disk method, but notice in this example, I'm not asking you to revolve around the line y equals 0 or the x-axis. I'm asking you to revolve around the line y equals 2. So again, I've already drawn the picture for you, but I always suggest that you draw a picture so that you can visualize what's going on. It's very difficult to do if you don't do that. So here I have the function f of x is the one on the top, which is negative x squared plus 2x plus 5, and then g of x is this line, which also happens to be the axis of revolution. Y equals 2, g of x equals 2, same line. So that's going to be key, because when we get to the washer method, those two things are not going to be the same. So here I'm now trying to find the volume of the area that I've shaded in green. And again, it's a 2D picture representing a 3D object. So we're going to go back to what we learned before about area. And remember, if I were to find the area of this figure, so the part that I have not flipped over, if I were going to find the area of that, I would take f of x minus g of x, and I would integrate with the limits of integration. That's exactly what we're going to do, is we're going to subtract just like we did before. So before we get into all of that, let's go ahead and find those limits of integration. So we got to find the limits, which means I'm going to set negative x squared plus 2x plus 5 equal to 2 and solve. So I have negative x squared plus 2x. I'm going to actually change the signs there because I like that first one to be positive. So positive x squared minus 2x, and then I would end up with plus 3, so I'm going to write it as minus 3 equals 0. Now I'm going to factor numbers that multiply to negative 3 that add to negative 2, which is of course negative 3 and positive 1, which means x is going to be positive 3 and negative 1. Those are my limits of integration. And again, I can verify by looking that this does occur at negative 1 and this does occur at 3. So from here, now I'm going to integrate. Now, because this video is already like 19 minutes long almost, I'm just going to start using my calculator to finish the integration. So I'm going to set it up, but I'm going to use my calculator, but I trust that you would be able to do the integration by hand. So again, to find the volume, I would have pi, and then use my limits of integration, negative 1 to 3, and then my function, again, we're going to take f of x minus g of x dx. So in this case, again, from negative 1 to 3, f of x is negative x squared plus 2x plus 5. I'm subtracting 2. And I am going to do a little bit of simplification. Oops, I'm forgetting my squared here. So now I have from negative 1 to 3 of negative x squared plus 2x plus 3 dx. And I'm not going to show any more work besides that. I'm just going to let my calculator do the work. just for the sake of time, and so my volume is approximately 107.233 cubic units. Again, just pay attention to what the instructions ask for. If they're okay with a rounded answer, use that calculator. If they're not, you would have to obviously square all of this, which would take us some time, and then do the integration by hand. For this example, I would really like you to try it on your own first. So it's very similar to the last example that we did. Notice I have not drawn the picture for you because I want you to get into the habit of drawing the picture yourself so that you know which function is on top and which function is on bottom, just as we did in section 7.1. So once you've had a chance to do this question on your own, press play to see how you did. So again, the very first thing that you should do is to draw that picture. Again, feel free to use Desmos. You do not have to draw it by hand unless you're asked to draw it by hand. Now, of course, I will ask you to draw it by hand, but you can cheat and use Desmos and then just sketch it very quickly, just so we know exactly what we're dealing with. So again, the first thing I need to do is to find the limits of integration. So to find the limits, I'm going to set the two functions equal to one another. So 2 minus x squared equal to 1. There's my first function, there's my second function. Now again, I want you to notice in this question, I've labeled one f of x and one g of x, which happens to be the order in which you would do it, but just don't assume that's always going to be the case. So that's why you need to graph it so that you can see exactly what you're dealing with. So again, to find the limits, I now have, I'm going to move the x squared to the other side, so I have x squared, and then I have equals 1. And so x is equal to plus or minus the square root of 1, which is just 1. So those are my limits of integration. Now I'm going to integrate to find the answer. Remember, when I integrate to find the volume, I'm taking pi, and then the limits of integration, -1 to +1, and then my function is f of x minus g of x, which is the correct f of x and g of x in this example. So 2 minus x squared, and then minus g of x, which is 1. That quantity squared dx. So again, just doing some simplification, I get 2 minus x squared minus 1, so that gives me 1 minus x squared, quantity squared, dx. Use your calculator to do the heavy lifting once you have reduced it to this point, which is what I've done, and we find that the volume is 3.351 cubic units. Again, yes, I could obviously multiply that out. I'm just trying to keep this video under 30 minutes. For the last example of this video, I wanted to do a question where we're revolving not around the x-axis, but around the y-axis. The good news is everything really is going to be the same. We're going to be revolving around a different axis, and so we have to sort of, in our minds, think of the representative rectangles going this way instead. But again, it's going to be the same figure. When I'm finding my limits of integration, I'm looking at the y-axis instead, and I'm going to integrate with respect to y. But really, you should notice that this example is going to look almost exactly like our last example. So just as I did before, I need to find the limits, and that's going to happen by taking the two functions and setting them equal, and that gives me y squared is equal to 1 and y is positive -1. And then I'm going to integrate, and I'm going to integrate with respect to y. And so notice f of y, g of y, it's already in that correct format for me. So when I integrate, I'm going to take pi from -1 to +1, and this is going to be the radius of y dy, and the radius of y dy is going to be, again, not the top minus the bottom, but the right minus the left. That's what we do when we go in that direction. So the right is 1 minus y squared, and the left is 0 dy. I always forget that squared, I apologize. So the volume then is pi (-1 to 1), just doing some simplification, 1 minus y squared, quantity squared dy. Again, I could multiply that out very easily, but just like on my last example, I'm going to let my calculator do the work, and I'm still going to get exactly the same solution that I had on my last question. Because again, I was using the same limits of integration and the same function, just with y instead of x. Coming up next, we're going to take a look at how to find the volume using the washer method.